so VP35 is another one of these. This one I was very charmed to see because this is very thinly veiled Diffie-Hellman handshake. This is what's really used to make cryptography work over the internet. And we've been doing modular arithmetic, so you begin to see some of the math you need for modern internet cryptography, and that's what's going on here. So we have a handshake. This is the Diffie-Hellman handshake in a nutshell. So you have a hotel room key, and the room key is an RFID card. You swipe it, and the light turns red. So you call the help desk, and they say, yeah, you'll have to get a replacement card, which is too inconvenient, or reverse engineer it. So you're going to reverse engineer the cryptographic handshake. So here's the handshake. Now, if you have a really simple card, like a payment card at like a Kinko's, you pay $5, you get a card, the card just says $5. When you buy something, it says $4. People showed this. Therefore, you can just write on the card $50 and get free stuff. So that is really, really, really primitive and only used for really non-serious applications. For anything serious, like a BART ticket, you do it this way. The card does some kind of handshake. This is what the card chip in your credit card does, the chip and pin. It doesn't memorize your credit card number and repeat it to the terminal. It does an exchange to cryptographically prove that it has the key, and especially Apple Pay does that. That's why I got a better phone to get Apple Pay. Apple Pay sends a different number every time. It never sends your credit card number at all. It sends a different cryptographic number to prove that you are in fact authorized to spend money for one transaction of this amount that cannot be repeated, which is much superior to the old magstripe or rubber stamp credit card things. So this is a simple case of this. So the card and the door are both going to perform an operation that transforms a subject number. So you start with 1, then for a number of times called the loop size, you multiply it by the subject number, and then you take the remainder, dividing it by 2 by this number. Now, this is a long-winded way to say you raise it to a power subject number, and then you take it modulus this, which is exactly how Diffie-Hellman works. Yeah?
So you're saying that the chip on the credit card is safer than the magnetic strip?
Much safer than the magnetic strip, and Apple Pay is much safer yet.
So you'd much rather insert it for the chip rather than swipe it?
Yes, the magnetic swipe just types in the number on the front page of the card, and we've been using that for decades, but that means the merchant can just keep drawing any amount of money forever. It's amazing. All security of credit card transactions in America for decades has been done at the server side. There's no actual prevention of people making fraudulent charges. In fact, it's extremely easy to. You can just go in the trash can and pick up the carbon paper. And they detect it all by detecting suspicious transactions at the server side, and they're very effective at it. It's a strange policy. Europeans had a different policy. Now we're moving towards it with chip. But if we were in Europe, we'd have chip and pin, which is much more secure. You have to have the chip, which proves you have the card, and you have to have the pin, which means you are the right user. That would be a lot more safe. But in America, as you might expect, the number one priority of everybody is to make it easier to spend money. And accepting more fraud to make it easier to send money is the way to make more money here. It's like I was discussing in another class a few days ago. This is why Ethernet won over Token Ring. Token Ring was a logical, organized networking protocol where every networking device would wait for a token and not send data until it got the token. And then when it was done, another person could send data. So if you had a Token Ring network running at 4 megabits per second, you could really send 4 megabits per second of data. Ethernet, every device just spews network data out without regard for anything, frequently collides with somebody else's packets and the data gets corrupted. Then you have to retransmit it. So you can in fact only get up to about half of the rated speed before it doesn't work anymore. But that turned out to be a winner in the marketplace. The fast, sloppy thing that was cheaper actually won over the organized, logical thing, which was too expensive. Anyway, so this is what we have. So it's going to do this transformation on the card, and the door is going to do the same thing. So the card always uses a specific loop size. The subject number is 7. It'll use a secret loop size, and this creates a public key. The door takes the subject number and transforms it using the door's loop size. That's the door's public key. Now they trade public keys, and this is exactly how Diffie-Hellman works. The public keys are not secret, and that's the only thing you send over the wire. But then each one of you combines the public key from the other person with your own private key. This is the Diffie-Hellman technique, and then you'll end up with the same encryption key. So this is a way to describe it with a card in the door. This was the miracle. This is what made public key cryptography work. I choose 2 random numbers, a public key and a private key. They're mathematically related. And if you multiply your private key by my public key, you'll get the same answer as if I multiply my private key by your public key. So we can agree on an encryption key without ever sending that encryption key over the wire. All we send is 2 public keys, which are mathematically related to the encryption key, but in a way that it is essentially impossible to derive the encryption key from that. And that's what we're all using on the internet now. This was the miraculous public key encryption that became published in the 1970s. Before that, it was a military secret, and made possible to send secrets over the internet without ever having a way to distribute the key in the first place, which is extremely powerful. That's what's going on here. So you have a challenge here where you figure that out. You know the public key. You can deduce the private key from it, and you can make a handshake. So this is pretty simple math, pretty simple code, but the concept is super important. The concept underlies all the cryptography on the internet right now. And by the way, it is in serious jeopardy, because the thing that makes it secure is that you cannot find the private key from the public key. And the most common system, at least the original system, was RSA, which I mentioned before, where the private key is a prime number, and you multiply it by another prime number, and the public key is the product of those two. So the difficult math problem that keeps it safe is that you cannot break a long number into its component primes. But that is not true anymore exactly. It's currently not possible to break it, but quantum computing, there's an algorithm called Shor's algorithm. If we had a good quantum computer, we could factor those prime numbers. So everybody's moving away from RSA and all other current public key systems that are similar to it, and moving to new systems that are just being developed and refined and certified by the government now. Because if quantum computers get 1,000,000 times better than they are today, then they'll be able to blast right through that stuff. And the way they're improving, people expect that will happen within a few decades. So our current crypto systems are going to have to change, and they always have, by the way. All the cryptographic systems keep changing every few years. That's why if you want insecure stuff, just find anything that hasn't been updated in about 10 years, and it will be full of awful flaws, because it's just the state of the art. People just didn't know about things, then they found out things. Every few years we seem to find something that renders the previous generation of encryption unsafe. Yeah?
I think you said before that you don't expect quantum computing to get the backcode that soon.
Quantum computing probably will. What I don't think will get a whole lot better is AI. We'll see. But the main thing to know is quantum computers are not that good yet. However, they are improving. I don't see any reason to doubt that within 20 or 30 years they'll be able to crack RSA. But people argue about it. You're projecting the future, of course. It's a guess. The thing I really don't believe is what the AI people say. The AI people say within a few years we're going to have artificial general intelligence as smart as a human, and within maybe 10 years we're going to have a super intelligence that's smarter than a human. And I don't believe that at all. I don't think either of those things are going to happen for many decades, and maybe not at all. Yeah?
Do you think there's ever going to be a point where they want to start listening like chips or something?
What's that?
Like, do you think they're ever going to have like digital chips inside like our arm or anything like that?
Oh, one of my friends has those things implanted. You can totally take those chips and implant them in your arm, just instead of carrying around a card. It's the same thing that would be in the card.
So that's already going on?
Oh, yeah, people already do it. I don't think they do it. I heard that if you have if you're on Homeland Security and you're working against the Mexican drug cartels, they implant a chip in you so they can find you if you get kidnapped.
Oh, wow.
And but I know this is something you have at every hacker convention. They'll plant those chips, and a lot of hackers do it.
That's crazy.
Just so they don't have to carry around. Well, it seems kind of fun, yeah, but there's a whole body modification village at DEF CON. There's people people that go crazy with like piercings and all kinds of stuff, embedded jewelry, and embedded electronic jewelry, of course, for hackers. Yeah, there's people that love that stuff. Yeah, I got a friend that's got a few of them implanted. There's people that implant magnets in their fingers, so now you can feel magnetic fields. Oh yeah, there's tons of it going on. I'm not in a hurry to do it. Of course, Elon Musk wants to put a chip in your head and connect you to the internet. I thought that sounded pretty cool, easier than carrying around a cell phone, until I found out it doesn't work and it kills the monkeys. So I decided I'm not going to be first in line for that, or for going to Mars. Yeah.
Interestingly, they did trial it on a paralyzed man, and that seemed to work pretty all right.
It worked for a few weeks and then it failed.
Thing is, I don't think I'd ever want to put one of those things in there, because anything electronic can be hacked.
That's true. It can be hacked. It can also fail. So you do it for people that have a serious medical problem, so they're willing to take a risk. But it's way far from being like tattoos, where a normally healthy person would feel like it's okay to get it just to make me a little better. I was thinking, get the Google chip, do Google searches, and just by thinking about it, that sounds awesome if it actually worked and if it was safe. But it doesn't really work, and it isn't really safe, not yet. But that'll probably happen. In a decade or two, everybody will probably be doing that.
And God knows you're going to try to play ads.
Oh, of course. Yeah, I can see that. You'll have ads popping up in your visual field from the implanted chip. Boy, that would be annoying. And of course, then you'll have the fascist government controlling your mind through it, filtering your news and stuff. Oh no, don't look at that video, look at this video. Anyway, all right, let me stop this recording.